Hi everyone! I'm Ananya, and today I'm going to be talking about leetcode 4, median of two sorted arrays. Okay, so let's read the problem. Given two sorted arrays nums1 and nums2 of size m and n respectively, return the median of the two sorted arrays, and our overall runtime complexity should be O of log m plus n. So they've given us two examples here, where the first array is 1, 3, second array is 2, and the median is going to be 2. Alright, and we also know that the nums1 length and nums2 length are going to be less than 1,000, and all of the values within the arrays are going to be within absolute value 10 to the 6th. So I think the line that gave me the biggest hint on where to at least begin is the overall time complexity should be O of log m plus n. Anytime I see that, like where they tell us that the ideal time complexity is going to be O of log m, I immediately think binary search. Especially in this problem, we have two arrays and I'm seeing O of log m plus n, which is the equivalent of log m times log n. So I'm thinking binary search of a binary search. So the first step I'm going to take, and this is just my rough logic here, is I'm going to binary search for a partition, and then I'm going to check to see if this partition is valid. So let's take up some test cases and see if this logic can hold. So in this first example that I've written down, I have two arrays. The first is of length 3, the second is of length 4. And I've also drawn my total array of length 7 with a partition marked where I believe the median should go. So what I'm going to do is I'm going to start running my binary search on the smaller array. So I have my low and high pointers marked, and I'm going to run low plus high over 2, which is equal to 1 in this case. So I'll just take the middle element along with the upper half of the array in this case. So right now I've drawn my partition with 2 elements on one side and 1 element on the right side. And when I look at my total array, I know that now I've reserved 2 spots for the 2 in the upper half and 1 spot for the 1 in the lower half. So knowing this, I know exactly where I need to split my second array such that we have reserved 2 elements that can go in the available spaces in the upper half and 2 elements that can go in the available spaces in the lower half. So we have a pretty much even split down the middle of the second array, and now is where I'm going to start checking to see whether or not this split configuration is valid. The max one is going to be equal to the maximum value on the left side of the first array. The minimum one is going to be equal to the minimum value on the right side of the first array. Likewise, the same logic applies when I label max 2 and min 2. So now what I need to check to see is if max 1 is less than or equal to min 2, and if max 2 is less than or equal to min 1. If both of these conditions are met, then I can say that we have a valid configuration and we can return the median, which we can identify by knowing the fact that the median is going to be in the left side of the array of the partition split, and we can just return the maximum of max 1 and max 2 because one of them is bound to be the median in this case. Okay, so the last example that I showed you was really basic because we didn't actually have to modify any of the low and high pointer locations, but this time I've intentionally falsified one of the conditions and I'm trying to simulate exactly what I would have to do in each case to see when I have to move which pointer. So in this case, we've started out with 2 arrays. The first is of length 1, the next is of length 3, and I've also drawn out the total array with the line in between to show where the 2 values we have to average to return the median are. Now, we're going to start off by running the binary search. We have the low on index 0 and high on index 1, and when we calculate the median, we find out that the partition actually goes at the very right edge of the first array, meaning that the 4 goes on the left side of our total array, and we have 1 space left on the left side and 2 spaces left on the right side, which allow us to understand exactly where we need to partition the second array between the first 2 indices. Now what we're going to do is we're going to insert the max 1, min 1, max 2, min 2. Max 1 is going to be 4, min 1 is going to be an arbitrary very large value which will always satisfy the second condition, and max 2 is going to be 1 and min 2 is going to be 2. Now if we were to compare max 1 and min 2, we actually see that the first condition is falsified because max 1, 4 is much greater than min 2, 2. So when we run into a case like this, we realize that we have to now shrink the searchable list by moving the high pointer down to median minus 1. When we do this, we end up having low and high equal each other, which is 0, and we understand that when we run the binary search iteration again, we'll have to find out that the new partition, it's going to be at the very leftmost edge of the first array. So 4 is going to be on the right side of total, and we have 1 space left on the right and 2 spaces on the left, meaning that we have to split the second array with the partition being between the second and third indices. Now, when we assign max1 to the smallest possible value, -1e6, and min1 to 4, then we assign max2 to 2 and min2 to 3, and we compare max1 min2 and then max2 min1. We realize that both conditions are satisfied, and now we can go ahead and return the median value by doing the maximum of the maximums plus the minimum of the minimums over 2. So the last case I have to show you is when max2 is greater than min1. So in this case we have two arrays. The first is of size 2, the next is of size 3, and I also have the total 5 element array drawn with the line in between to represent where the median would go. Basically, we start off with our binary search where we put low and high to be 0 and 1, and when we calculate the average, we find out that the first array gets split right down the middle, leaving one element taken on both sides of our total array. Now we know that there's 2 elements that we need to put on the first half of our array and 1 element that goes in the last, so we know exactly where to split the second array, write down the elements 2 and 3. So in this case, we can assign our max1 to be 2, our min1 to be 2, our max2 to be 3, our min2 to be 6. When we compare min2 and max1, we find out that the first condition is at least satisfied. However, when we compare max2 and min1, we realize that 3 is actually greater than 2, which falsifies the second condition. In this case, what we can do is we can move low up to become median plus 1. When we re-average the entire binary search iteration, we find out that the new partition for array 1 would go on the very rightmost edge, making max1 2, min1 an arbitrary very large constant, and then max2 1, min2 becomes 3. And when we compare max1 and min2, and then max2 and min1, we find out that this is a very valid configuration for us to then just take the maximum of the maximums that we have and output that as our median. Okay, so after 3 examples, let's start coding this. The first thing we're going to do is we're going to make sure that we're actually only doing binary search on the smaller of the 2 arrays. So if the arrays come in and nums1 is greater than nums2, let's just make sure that we swap them. So if nums1.size is greater than nums2.size, then we can just return same function called, but swapping nums2, nums1. Okay, now we can start coding some binary search. So int low equals 0, high equals nums1.size. What about this? Int part1, part 2, which are going to be our partitions, max1, min1, max2, min2. Alright, now while low, this is just general binary search, while low is less than or equal to high, then we can call part1. We know part1 is going to be equal to low plus high plus 1 in this case over 2, because when we're trying to force the median value, if there's ever like an odd number of elements and we want to force the median value to be in the upper half of the array, we basically need to use the ceiling function here, where it's almost like you're doing 0 plus 5 over 2 equals 2, but 0 plus 5 plus 1 over 2 equals 3. Alright, now let's put part 2 in there, where we do nums1.size plus nums2.size plus 1, this is just finding the median of the total array, minus how many ever elements we've already allocated for the left side, which is just the number of elements in part 1. So now what we have to do is we have to calculate the max. So max 1 is going to be dependent on where part 1 actually is. If it is like all the way on the left side, then we have to make max 1 equal to int min so that it satisfies the first condition. Or if not, then nums1 is going to equal part1 minus 1. And then min1 is going to have similar logic, where part1 is equal to, if it's all the way on the right side of the array, then it's going to be int max. If not, then it's just going to be part1. Okay, I believe all of this logic can be copy-pasted. Part 2, let's change this one to 2, 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 2. Alright, so everything has been changed, I believe. There are no ones in there. Alright, and now we can begin the logic. If max 2 is less than or equal to min 1, and, min 2, and max 1 is max 2 is less than or equal to min 1, then what we can do is we can just return the median, which in our case, let's say nums1.size plus nums2.size divided, like, mod 2 is not equal to 0, meaning there's an odd number of elements. What we can do is we can just return max of double max 1 double max 2. Alright, now in the off chance that there's an even number of elements, what we need to do is return max, like, .0. Now here it's going to be maximum of, I guess this entire line can just be copied, or min 1 double min 2. Alright, so that should be the entire logic for that line. Now there is one case where we have to move the high pointer. Let's just write that one in. If max 1 is greater than min 2, then that means that high equals part 1 minus 1, else equals part 1 plus 1. And now we can just, if nothing argument failed. Alright, this should be good to me. Let's run it to see if we did anything wrong. Alright, so those cases passed. Alright, perfect. So that is my solution to problem number 4.